So for today's algorithm, we're going to be talking about number systems, specifically binary and decimal. But before we get into the distinctions between the two and how you convert from one to the other, we need to first define a notion of what we mean by a string of decimals or a string of digits. And what that means is, what does it really mean mathematically when we write a string of digits one after the other? So we define this notion of xn concatenated to x1 as a sum from I equals 1 to n of the cardinality of d, which we'll define in a second, times I to the power of I minus 1 times xi. So what is d? Well, d is the cardinality, or d is actually the set of digits in the number system that we're working in. So as an example, in decimal, the set of digits is 0, 1, 2, 3, 4, 5, all the way to 9. We know that the cardinality of this set is 10. So the cardinality of d is 10. And therefore, the basis of our number system is 10. So as an example for what that means for this summation, we'll take the number 957. So 957 can be written in a decimal expansion as 9 times 10 to the power of 2 plus 5 times 10 to the power of 1 plus 7 times 10 to the power of 0, using this sum notation. Now, this leads us directly into binary. So the first thing we need to know when discussing binary is, what is our set D? And our set D in binary is 0, 1. Naturally, the cardinality of this set is 2, so 2 is the basis of binary, or 2 is the basis of the number system binary. So let's take an example in decimal, expanded in decimal, expanded in binary, and then turn that back into a binary representation of the number. So let's take the number 13. 13 in base 10. So 13 in base 10 can be written as 1 times 10 to the power of 1 plus 3 times 10 to the power of 0, which equals, in the binary expansion, 2 times 2 to the power of 3 plus, or 1 times 2 to the power of 3 plus 1 times 2 to the power of 2 plus 0 times 2 to the power of 1 plus 1 times 2 to the power of 0, which by dropping the 2's, we see that this is equal to 1, 1, 0, 1 in base 2. So you're probably wondering at this point, well, how do you actually find this binary expansion? Well, we have an algorithm to find this binary expansion, which works as follows. What you're going to do is you're going to look for the largest power of 2 that fits into your decimal number. And then you're going to consider how many times that number can fit into your decimal number. This will be best explained by an example. So let's take the number 17 in decimal. 17 in base 10. We want to know what is the largest power of 2 that fits into 17, and that number is 2 to the power of 4. So we have 1 times 2 to the power of 4. We want to then know how many times can we fit 2 to the power of 3 into this number, and that is 0 times. So we say plus 0 times 2 to the power of 3. Next, we want to know how many times can 2 to the power of 2 fit. So that's 0 times 2 to the power of 2. And 2 to the 1, that's 0 times 2 to the power of 1. And lastly, how many times can 2 to the power of 0 fit? And that's 1 time. 1 times 2 to the power of 0. We notice at this point that 16 plus 0 plus 0 plus 0 plus 1 is 17, which is our target number. So that means we stop here and we strike the 2's, which leaves us with the binary representation 1, 0, 0, 0, 1. Now that we've converted from decimal to binary, what's left is to convert from binary to decimal. Now this is going to be much easier than the other way around, but we have an algorithm for this as well. So this is best explained with an example. So let's start with the example 1, 1, 1, 0, 1, 0, of course in base 2. So what is our algorithm going to do? we first have to find the largest index, so the value of n for x sub n, in this string of digits. So we're going to count from the right. So we're going to have 1, 2, 3, 4, 5, 6. Now we know from our sum notation that this means that the farthest number to the left is the value at that index times 2 to the power of the index minus 1. So we can write this as 1 times 2 to the power of 5, 6 minus 1. And the same goes for 1 times 2 to the power of 4, and 1 times 2 to the power of 3, and 0 times 2 to the power of 2, and 1 times 2 to the power of 1, and 0 times 2 to the power of 0. And now using decimal arithmetic, we can just compute this as 32 plus 16 plus 8 plus 2, which is going to equal 40 plus 18, or 58 in base 10. 58 in base 10. Which is going to equal 58 in base 10. So the next logical step from here is, well, how do we convert fractions? Well, let's first consider what a fraction is in decimal. So in decimal system, we denote a symbol, the period, to indicate where the powers are negative and where the powers are positive. So everything to the right of the period is a negative power, and everything to the left of the period is a positive power. So let's take as an example the decimal number 9.25. So the decimal expansion of this number is pretty simple. It's 9 times 10 to the power of 0 plus 2 times 10 to the power of negative 1. We know it's negative 1 because we are now on the right side of the period, plus 5 times 10 to the power of negative 2. Now let's find the binary expansion of this number. So we're going to use the same algorithm as before, but now we have to make a slight modification to our summation. So now we can actually go beyond 1. We actually can go negative in accordance with the number of negative numbers to the right of the period. So let's take 9.25 and apply the algorithm with a slight modification. So first we find out how many 2 to the power of what can fit into 9. And we notice that 1 to the power of 3 can fit into 9. So we write 1 times 2 to the power of 3. And then we notice that we can fit no 2 to the power of 2. So we're going to say 0 times 2 to the power of 2 and 0 times 2 to the power of 1. But we can fit 1 to the power of 0 to get us 9. But we still have some left over to reach 9.25. So now we're going to check how many 2 to the power of negative 1s can we fit? Well, we can fit 0 to the power of negative 1s because 2 to the power of negative 1 is 1/2, and 1/2 is larger than 1/4. And 9.5 will be larger than 9 1/4. So then we check how many 2 to the power of negative 2s can we fit? And we can fit 1 2 to the power of negative 2, which gives us exactly 9.25, which means we can now strike the 2's and write this in binary as 1 0 0 1 0 1, and place our period customarily between the inner 1 and 0, where the positive powers switch to become negative powers. All right, now let's take an example in the other direction. So let's take the decimal number, or the binary number 10.1, and convert that to decimal. So this is base 2, of course. So we're going to use the same algorithm as before. So the largest index we have here is 2. So our first number is going to represent 1 times 2 to the power of 1, plus 0 times 2 to the power of 0, plus 1 times 2 to the power of negative 1. We can compute this using decimal arithmetic to find that this is equal to 2 and 1/2, or 2.5 as we write in decimal. So now that we have this framework for understanding number systems, we can actually expand it to any number system that we choose. We're no longer limited to just binary or decimal, because now we have a formula for figuring out how we need to compute, convert, and do other operations in this number system. So just as proof of concept, and for the sake of this video, let's choose the number system ternary. Ternary has a set D equal to 0, 1, 2. That is, the digits we're allowed to use are 0, 1, and 2. Now, the cardinality of that set D is clearly 3. So, in order to convert and compute decimal to ternary and ternary to decimal, we're going to have to modify our previous algorithm slightly. But first, as an example, let's give an example that does not require modification of the algorithm. So let's look at 9 in decimal. And let's try to convert that to ternary. So 9 in decimal can be converted as follows. We can fit 1 times 3 to the power of 2, plus 0 times 3 to the power of 1, plus 0 times 3 to the power of 0. We strike the 3's, and this leaves us with 1, 0, 0, and base 3. But now let's look at an example that requires a modified algorithm. Let's look at 23 base 10. We want to know not what largest power of 3 can fit into 23. We want to know how many of that power of 3 can fit into 23 as well. And the amount of times that number is allowed to exist is any number within the set D that we defined above. So that means we can either have 1, 2, or 0 of that power of 3. So we're going to use the same algorithm now with this slight modification. We're going to check what is the largest power of 3 multiplied by some number of D that can fit into 23, and that's 18. So we're going to write 2 times 3 to the power of 2 plus. So now we're at 18. We want to know how many times can we fit 3 to the 1. We can fit it once, so we're going to write plus 1 times 3 to the 1. And now we're at 21. So now we need to know how many 3 to the power of zeros can we fit. And we can fit exactly 2. So we're going to write plus 2 times 3 to the power of 0. We strike the 3's to write 2, 1, 2, and base 3. So what about decimals? What about fractions? Well, let's take an example from binary. So let's take the binary number, the decimal, sorry, not from binary, from decimal. Let's take the decimal representation of 3 1/3. So 3.333 repeating. What you'll notice here is that 3.3 repeating, or 3 1/3, can actually not be represented in the decimal number system. But what you're going to find is that it can be represented in ternary, which implies that there actually is some advantage to switching between number systems. Let's say, for example, you have some application that uses thirds or ninths or something else that cannot be represented in decimal. Perhaps you want to switch to a number system that can handle those kind of fractions. But to prove that this is the case, let's actually convert this into ternary. So we have 3 1/3, 3.3 repeating. We're going to use the same algorithm as before in order to convert this to ternary. So we want to know how many 3's 3 to the power of 1's can fit into 3.33, and that's exactly 1. So 1 times 3 to the power of 1. But now we're to the right of the period, so we need to now consider negative powers. So, well, not yet, actually, because we first need to know how many 3 to the power of zeros can fit into 3, and that's 0. So we're going to say plus 0 times 3 to the power of 0. And now we're to the right of the period. So now we need to consider how many negative powers can fit into 3 1/3. And it turns out that exactly 1 negative power of 3, so 3 to the power of -1, can fit. So we say plus 1 times 3 to the power of -1. And we've reached our target. We're now at 3 1/3. So we can strike the 3's and write this as 10.1, customarily putting the decimal between the power of 0 and the power of -1. So thanks for watching our video on number systems. I hope you came away with understanding more than just binary and decimal, but really how number systems work in general. And with this knowledge, you can now use it to consider and figure out for yourself how you might do addition, subtraction, multiplication, and any other operation, because it all comes down to how these numbers are represented. Thanks again for watching. Don't forget to like, favorite, subscribe, hit the bell icon in the bottom left-hand corner, click the link in the description if you want to follow on Patreon, and watch our next video, which will be right over here. See you next time.